everybody. I go on, starting from the very last part, my previous presentation. Let's start with a picture, so to say. The idea was possible evolution equations in the form of memory kernels, building on classical intuition, in analogy to what has been done in order to obtain quantum dynamical semigroups, building on classical Markovian semigroups. Now, the situation was as follows. We have think of a classical particle that can jump in between a certain number of sites, just draw a few. And the idea is that you have once you are in a given site, say 1, you have a certain probability to jump to other different sites, and these probabilities are encoded in a so-called stochastic matrix. Stochastic matrix, let me remind you, it is a matrix which sends a probability vector into another probability vector. So it's the natural transformation which preserves positivity and probability in a classical setting. But on top of this, as we said, we have also a degree of freedom which tells us at which point in time our particle is going to jump. And as I mentioned yesterday, there is a special expression for this function, which is typically called waiting time distribution, since it gives us information about when the next jump is going to occur. A very special form, which is the exponential one, which drives us back to a Markovian description, which means that it doesn't matter how long you have been sitting on a given site to give you information about when you're going to jump next. Now what we will do is to allow both for a generic transition matrix and for a generic waiting time distribution. These two ingredients are enough to provide us with a general class of processes which in the classical setting are non-Markovian, and we will try to build on this intuition in order to obtain quantum processes which might feature non-Markovian dynamics. What I actually mean by non-Markovian dynamics, I'm going to explain later on, but for sure you can get an intuition that we are going beyond the simple semigroup composition law, in which in order to proceed forward in time, you only needed to know the state at a given time. So I wrote yesterday the integral differential equation obeyed by the probability vector P of t. And in that equation, which can be written for a single elements for the single components of our Pi of t, we have an equation in integral form with certain transition rates, which I wrote as Wji depending on time, and the rest is as I wrote yesterday. The point is that this transition kernel in the classical setting is a simple expression in terms of those objects once you write it in Laplace transform. So the Laplace transform of this kernel, which as I used yesterday will be characterized by a hat as a function of u, depending on two indexes, can be written in terms of the matrix element Ji of our transition matrix times the ratio between the waiting time distribution, depending also possibly on site, so the one related to site I is a function of u, divided by the survival probability at the same site, G of u. Now, this is what we learn from the classical setting, and now the point for us was, given that we have the classical master equation for our probability vector, which I recall from yesterday in Laplace transform can take this expression. This amounts right to the derivative of the nth component of our probability vector is equal to the action of some kernel that we want to envisage acting on the Laplace transform of the probability vector. And here we have a kernel which will depend on the site and sum over m. So now we have some insight from the classical viewpoint of how this object might look like. I've already given the explanations. Let me write it more in detail. Here to the right-hand side, we would have a sum over m. The full contribution goes exactly as there. So we have our transition matrix pi and m, the ratio between survival probability, the Laplace transform of this quantity, the function of the site, divided the survival probability, the function of the site. And remember that the survival probability in time domain gives us the information not to have left the site up to the given time. So that's where the name survival comes from. That's this for the first part. And the kernel as a whole, you remember we had a gain and a loss term. So we have now fixed the gain term, and the loss term can be written as follows in this setting. Is a Kronecker delta Nm times 1 over g hat of u, the function of m, minus u. Everything multiplies with the Laplace transform of the nth component. So this is the expression of a classical kernel in Laplace transform. Of course, it's a complicated expression, but I've tried to give you some insight on it. Essentially, it is fixed, but it's two quantities which have a natural physical interpretation. Now, what do we want to do? Well, the idea would be go over to a quantum kernel. Part of the job is easy, since we want to move from classical to quantum. We know what to do out of our probability vector. This will become our statistical operator, the function of time here considered in Laplace transform. So the probability vector goes over to a statistical operator. This is clear. But what happens to our kernel? This is less obvious because we have to find quantum counterpart for all these components. And on top of these, once we get quantum counterparts, these will be operators, operator-valued objects. So this ratio doesn't have a unique meaning. It makes a difference whether we first consider the operator corresponding to F times the inverse operator corresponding to G or vice versa. So it also, operator ordering, as typically happens in quantum mechanics, can play an important role. So let us first write what is the replacement for a single object, and then introduce a law, let's say an operator ordering, in order to translate the kernel as a whole. The transition matrix, which sends, as I've written there, probability vectors to probability vectors, must be the natural transformation sending statistical operators to statistical operators. So in the language that we learned yesterday, this is naturally a completely positive trace-preserving transformation. Let me call it capital E. This is a CPT map in the sense I clarified yesterday. So this is the natural counterpart of classical transformation which preserve probability trace and positivity. Then we have this object, F, which in the time domain we write as F of t, our waiting time distribution, giving us information on when the next jump is going to occur, depending on site. So this is actually a collection of objects, as well as this is a proper matrix. And to this collection of objects, we have to associate an operator. We write it as follows. We consider a C-number part, which is just a fixed waiting time distribution, and an operator part, let me call capital F of t, where F of t is a collection, since for each t we have a different one, a collection of CPT maps. And then we have G, a whole collection of G depending on site. This will be defined by the survival probability which is associated to F in order to retain the connection among the two objects, and by a general collection of CPT maps, this G of t, which will have the same properties, so a collection of CPT maps, with a further constraint that for t equals 0, this map simply acts as the identity. In analogy to the fact that the survival probability that time t equals 0 is 1, since the system is starting from that side. So this is a kind of natural replacement, which sends classical objects to quantum objects, so a matrix transforming probability vectors to a map transforming states, that is to say statistical operators, and the same for the other objects. But on top of this, as I've said, this is not enough to say what is the operator which replaces this contribution. Here it is enough, because in the essence we have just one operator. So once we have fixed what this operator is, everything is fine. But here we have a product of functions. And the product of functions does not translate uniquely to an operator expression. So we have to make a choice to some extent. What we have to do is introduce an operator ordering. Let me call the letter O to note this factor. So we have to say what we associate to our classical object. And there is a certain freedom in doing this, so that we can allow for different operator orderings, as what happens is that different operator orderings lead to different quantum evolution equations. Each of these possible quantum evolution equations is well defined, but describe a different dynamics, which tells us that moving from the classical to the quantum setting, this approach allows still to introduce quantum processes, but these quantum processes, in a sense, provide a wider scenario with respect to the classical setting, because also the different order in the time action of the transformation maps do play a role in determining what is the solution. So now I will consider a point to a physical application of this scheme. There are other ordering which can be considered and that lead to different physical applications. Now the one I will consider here is to move this object to the left and keep the inverse of this operator to the right. So let me replace this by the stochastic matrix phi is replaced by this CPT map E. Then we have the Laplace transform of this object, the left, and the inverse of the Laplace transform of the other operator. This is enough to fix our quantum kernel. So this is enough to fix our quantum memory kernel master equation, which I will write as follows. I leave this here for a moment so that we can better see the analogy. So what we have is the derivative in time of our statistical operator associated to the reduced system, so the degrees of freedom we are interested in, is given by the integration over time between 0 and t over d tau of a certain kernel k, depending on t minus tau, acting on rho s times tau. And as I said, this can be equivalently written in Laplace transform, where this convolution simply becomes multiplication, so that it's easier to be handled algebraically, so that also the insertion of that kernel is much easier. So this is equivalent to the following relationship, which I wrote actually also yesterday. In principle, the statistical operator, the Laplace transform of the statistical operator time t, can be obtained by letting the following operator, which is the inverse of u minus the kernel on the statistical operator times 0. So in principle, if you know this object, complicated as it might be, you apply it to an arbitrary initial state, and you have the final state in Laplace transform, and then you have to transform back. So it's formally clear. Then the point is whether you are able to do this.
Ordering provides one dynamic equation.
Yes.
Which one to choose exactly?
This depends on the physics. As I said, depending on the chosen ordering, you describe a different physical situation. Now I will point to this one and connect this to the dynamics of a cavity mode interacting with atoms flying through the cavity. We'll do this in detail. And then I will not have time to go through other examples, but I prefer to to work this out in detail and then point to other solutions. Sorry? Actually, you cannot decide it, I would say, you cannot decide it coming simply from the equation from a mathematical viewpoint. The point is when you then insert definite expression from this object, if you have a given dynamics in mind, then the sequence of the different interactions is determined by the physics itself. So it's not something that you can decide beforehand. So beforehand, let's say from a strictly mathematical viewpoint, you can note this analogy and point to possible operator replacement, and then check whether these replacements do make sense in the precise meaning that they lead to well-defined dynamics. So it's analogy to saying, okay, you are given the Lindblad master equation, then how do you decide which kind of Lindblad operators you insert? This Lindblad operator should describe the microscopic interaction. So this will depend on the system you're going to describe. And here, in a sense, you have a larger freedom. You have both the description of the interaction and keeping into account that the different interactions happen one after the other, and the sequence of these interaction events will determine different dynamics. So it's something which have actually to be fixed, having in mind a given implementation. Yes, please. I've said that different orderings lead to well-defined equations. This doesn't mean that simply consider a mixture of the different orderings would lead to a well-defined equation. Because now what you have in mind, since I stressed the connection between classical and quantum, the problem of ordering, then you are focused on something like, well, I need Hermitian operators, for example, so I try a symmetric combination, this is dimensional candidate. Yeah, I'm looking for something else, in a sense, a bigger constraint, is you have to look for operators appearing in the structure which lead to a kernel preserving both trace and complete positivity. So it's not that the single objects are well defined by themselves, these operators. And indeed, this is not a constructor which, in a sense, if you take the self-adjoint, it's not the proper meaning, but if you go to the dual expression, the ordering changes, so it's a different issue that I'm addressing. Still relying on a choice of operator ordering, but a different issue. So the question, each object by itself is well defined. I don't have the problem that one would have if you come from a classical expression to a quantum one, that you have to take care of symmetrization in order to prepare the ground for a possible self-adjoint effect. So there are relationships, but the relationship lie actually more in the fact that when I move from here to here, I go from this is a function that can be seen to belong to an algebra of commuting objects, and here I move to operators or maps, which can be seen to belong to an algebra of non-commuting objects. This is the main fact. Okay, so that plays a role. Now, as I've said, now mimicking the classical setting, I'm looking for something which is valid in the quantum setting. So I insert the kernel here. I know that it is equivalent, so the proposal is to consider a kernel with a quantum maps in the Laplace transform where in some sense I'm guided by physical insight, some suggestion of how the dynamics might go on. This should be kind of quantum analog of saying my system as can interact with another one, can evolve for a given time according to a certain law, and so on and so forth. And this describes the dynamics is a kind of piecewise dynamics, if you want. Interaction, evolution, interaction, evolution. Only more complex than the one I described yesterday. So with a nice amount of algebra, in a sense, you can write down this kernel and obtain explicitly this expression, which I write down because it should be not so strange given what I presented yesterday. So the statement is that if you consider the time evolved state, take s of 0 and let it evolve, how does it look like? I have a first contribution that, in analogy to what I've written today, is the action of a kind of this is the analog of the relaxing interaction introduced yesterday. So up to the time of the first event, so to say, the statistical operator evolves according to this evolution map. This time evolution map, each of them is a completely positive trace per second, so this is a well-defined dynamics up to the time of the first event. Then I have a further contribution, which I sum from n going to 1 to infinity. In analogy to what you have seen yesterday, I start anyhow from the state at time 0, let it evolve up to a first jump according to this first map f times capital F. So this, in a sense, of course, I cannot take each piece of the equation and make a reasonment on it by itself. No, I'm just trying to convey some intuition. The interplay of all the single objects is very important. But here the idea is the states evolve up to time t1 according to this time evolution map, which might itself be a semi-group or something more complicated. So not necessarily something which is divisible or a semi-group or something like that. It's an arbitrary collection of CPT maps. And this C number part, in a sense, takes into account the time up to the insertion of the first event. And the first event, let me call it like this, that's the reason for using this letter E for this map, is a CPT map which describes a certain interaction taking place at that time. For example, here the time evolves, and here is something like a collision, a certain microscopic interaction. We'll come to an example in a minute. Okay? Then, again, there is evolution from time t1 to time t2, whose duration is determined by this function, then another event, and so on and so forth, till, in a sense, the last one, given the last event, the final part of the time evolution is driven by this mapping G, whose duration is determined by the C number function G. So this once and again, in principle for an arbitrary number n of times, and here I integrate over the possible times. So dtn goes from 0 to t, and dt1 goes from 0 to t2. The point is that these are nested integrals, meaning that this event takes place before this other event, and so on and so forth. This is, in a sense, exactly the expression that I wrote yesterday, only generalized. In which sense? Yesterday, all that I had was that this expression was this R of t, so this relaxing part. And this epsilon was a jump transformation. And there was a strict relationship among the two, which was necessary in order to preserve the trace, essentially. Now, I am allowing the fact that this is a general time-dependent transformation, and this is a general time, a general microscopic event, so a general CP map. And on top of this, I introduce dependence on the time elapsing in between events. So from this perspective, I hope this is somehow natural to be understood. It's a viewpoint which is in analogy to a possible expression of the solution of a Lindblad master equation, the one I wrote yesterday, only allowing for a generalization of the single pieces appearing. So a more general time evolution in between jumps which not depend in their form on the previous time evolution, and the distribution in time of the jumps. Now, one can check that indeed this mapping provides a completely positive time evolution, and this is easy because I'm composing the same reason as yesterday. I'm composing CP completely positive maps. So this remains completely positive, sum over completely positive, integrated different times. So this is The difficult part in this setting is actually trace preservation. And this preservation is warranted by the fact that each of these contributions is trace preserving, and these functions g and f are related in such a way that they essentially, if you would neglect the operator part, they would end up to provide a collection of numbers, Pn of t, which is the probability to have n events up to time t. This is a quantity which typically characterizes the so-called renewal process. The renewal process is the generalization of the Poisson process, in which you have counts at different time. In the Poisson process, there is a specific law which takes care of the time interval among the counts. If you take a generic law, that was the exponential law I mentioned yesterday. If you take a generic law describing the waiting time in between counts, you obtain what is called the renewal process. So it's a process describing number of counts up to a given time. So number of jumps, number of interaction events, number of radioactive decays, or whatever. Okay, so this is the idea. And in a sense, I'm merging ideas coming from different classical processes to obtain a situation which has many degrees of freedom, so to say, which allow you to consider quite general dynamics. So let me come to an example in order to provide the possible physical insight. Yes, please.
Some of the stochastic situations, compared to classical and quantum, for example, for passage problem and time of arrival problem, classical is very different, but in quantum there are many problems conceptually. So while going from classical stochastics to quantum stochastics, in this situation, do you find any such kind, any different or any other kind of conceptual difficulties?
Well, this is a subtle point. I will come back to that later on, so that maybe it's better to discuss it later on, so the connection between classical and quantum. Let me stress the fact I insisted at many points that we took intuition from a classical setting, and then we're looking for possible sensible replacements. So I said I look for sensible replacements. I have further to introduce an operator ordering. This corresponds to the fact that it is not obvious for sure to go from classical to quantum. And then I said, then one can check that indeed this choice leads to well-defined dynamics. So in the end, I had to check that my intuitive correspondence actually led to a well-defined dynamics, to a well-defined quantum evolution equation. So it was not taken for granted. And this was just because one is aware that it is not obvious to go from the one side to the other. Anyhow, I would like to come back to this point in another perspective later on, but now it's not feasible. I should introduce too many objects. So in order to be precise, I come back to that today. But anyhow, this is for sure important, and indeed, you note how cautious I was in going step by step. And then in the end, I had naturally to check this, and this is essentially the check, so that I can explicitly write down the expression and indeed see that everything is in order, so that I can grant both CP and trace preservation. Of course, there are calculations that one should do, but this is in the essence. So I go for the example. And the example goes as follows. The dynamics one has in mind is a dynamics in which I have a cavity and a mode in the cavity, so electromagnetic field in a cavity. These are called the experimental situation, which is actually considered in setting is related to so-called micromaser mode. You are interested, so this is the system for you, the cavity mode. So it's in this case, just as a counterbalance, the other example is a system which lives in an infinite dimensional Hilbert space. No, it's not a spin. And what is the environment is setting? You have the freedom to prepare a beam of atoms which are sent through the cavity. So they arrive to the cavity. They are atoms which for the purposes of the cavity, can be considered as two-level atoms. So there are only two levels which are interested, so to say, in the interaction with the mode. They are sent to the cavity. They can interact with the mode in the cavity, and then they come out, possibly unchanged, or possibly they left the photon or gained the photon. So possibly unchanged or possibly actually interact. And the fact is that you can send these atoms one after the other, and there's a certain freedom in doing that. In particular, you can play on the waiting time distribution characterizing the atom beams. So you can consider a stationary beam which has, however, different properties, is not necessarily distributed as a Poissonian beam. So that indeed, the fact that an atom has just interacted with the cavity might provide you information about when the next atom is going to arrive. So this is the physics behind. So this is the system, and if you want the atoms in this case, so we are reversing the role in a sense. No? The system is the mode in the cavity, the one you want to study and affect in a sense, one you can measure later on. And the atoms are the way in which you interact with your system. Okay, you send atoms flying through, they interact for a certain time, and then you see what happens. So if I draw a kind of time axis, hoping it is long enough, so let's take a time, this is time t equals 0, and I have my cavity in the initial situation. This bad drawing is meant to be a mode in the cavity. Then, as written here, my system evolves according to a time evolution which are described by the mapping capital F. In this case, the time evolution is a semi-group cavity damping. So this is, in this case, actually a semi-group evolution. So the mode itself in the cavity undergoes damping according to a typically called Markovian description described by Lindbergh. So for the first time. Then at times T1, I put T1 here so that I have more space. What happens? I have my cavity, but the atom flies in, so to say, so it arrives, interacts with the cavity, and this interaction I denote, I describe through this map epsilon. Now I will comment on the structure of this map, and then it goes through and comes out, possibly in the same state. What is epsilon? Epsilon in this particular setting is a damped it's a James mechanics interaction lasting a given time which is taken to be fixed. It looks like the sensible approximation to take it as a fixed time. So epsilon is a transformation from one state to the other. You input one state, you let it interact according to the James-Mechanics Hamiltonian, which you can describe, provide the evolution then trace over. And since the time is fixed, it's just a one-shot transformation. So just one map. And then the dynamics goes on for another time up to another time, say, T2. So this is described by F T2 minus T1 times capital F T2 minus T1. And again, it's the cavity is isolated. There's only Markovian damping in the cavity. And then another interaction takes place. So another atom arrives, interacts with the cavity, and for example, in this case, we can suppose that it is modified. So has released the photon in the cavity. And the interaction is always described by the same map. Then time goes on, and I exploit the fact that you have a beautiful blackboard, so I can go on. There are many other interactions till the last one, say at time Tn. And the final part of the interaction is driven by this function g, 4 times t minus tn, and capital G t times minus tn, and this time evolution is actually the same as f. So it's not necessary to have different collection of time evolution maps for f and g. This is a freedom which you can have in your equation, which is also useful in certain application, but it's of course not mandatory. So in this case, the remains the same. So I hope this example gives you an idea of what might happen. So we have our system, which is the cavity mode, and the interaction is driven by a certain map which describes what happens before there are certain special events. The special events are described by the atom flying through the cavity. Of course, they should go this way, but never mind, no? I need to verticalize the interaction. After the event, again, the cavity is isolated, so the mode evolves according to its own dynamics, its own Markovian dynamics, another interaction, and so on. And depending on the expression of this interaction map, which in our case is the James-Cummings interaction, depending on what happens during the time evolution, so the dynamics itself of the mode within the cavity, and the degree of freedom which in a sense is available to the experimenter, that is to say, to determine when these times t1, t2, tn occur, so statistically, in a statistical sense, so whether they are exponential distributed in time or follow other distributions. This will depend on the preparation of the atomic beam. So depending on this, you have different effects on the reduced dynamics, that is to say, you have different effects on the cavity mode. So you end up with different preparations of your movement. Can be controlled to some extent, yes. Of course, don't ask me how exactly, no, I just go for the theoretical part, but this I found this as a nice possible. It's written in the waiting time distribution. Then G is fixed, so that is essentially F. So if it is an exponential function, then this leads to a distribution of arrival atoms which is Poissonian. For other expression, it's a general renewal process. That's where the freedom lies. Sorry? This information is contained in this part of the mapping. This gives you the dynamics of the mode in the cavity. Physical sense means this object can be written as T1 times L. This is a Limblad generator. And this Limblad generator is an example we have not seen yesterday, but one in which our Limblad's operator correspond to a dagger creation and annihilation mode. So, and then you have a certain gamma. Our gamma k goes to a gamma which is characterized the cavity decay time. So what happens is that you have your mode in the cavity at this, so roughly speaking, the excitation which you might have in the mode might go lost, so go out of the cavity. So you have not a perfect shielding, a very good shielding, which determines the time scales over which you can retain, so to say, in the cavity, but it's not infinite because, yeah, and of course, I mean, there is a huge literature on this micromeso model. I am certainly not an expert. No, I'm just focusing on the aspect which is relevant to this kind. But it's nice because there is a lot of I hope this example have clarified a few points. Now coming back to the fact of other orderings. Other orderings are interesting, for example, for so-called quantum collisional models. I'm not going to that, otherwise I run definitely out of time. But the idea there is that you can describe your dynamics always having in mind that your system interacts even times with an ancilla, let's say, in that setting. So your environment, instead of these atoms flying through, is composed of different ancillas, which might be independent or interact among each other. And the dynamics of your system in these collisional models is determined by the interaction of the system with different ancillas at different times. Then memory effect might come up depending on whether there is an interaction among the ancillas in between collisions, or, for example, in the time distribution of the collisions with ancillas. So this is another possibility. I will give you some reference, but I think it's better to work out one in detail then. So can I move on? Fine like this? Now I go for another, I still not introduced the tutorial part, so to say, for the Limblad master equation. I do it now with an example which is related to a collisional, still to a collisional dynamics if you want, but in a different set. So let me come to this. So in a sense, it is a simpler example. This one is obviously quite sophisticated. So as you've seen, in a sense, going beyond a standard Limblad approach. So here we are. So I go for example or tutorial if you want, number 2. Actually, I've tried to be as pedagogical as possible overall in the lecture. Still, I focus on some specific examples. Now, the idea is to give one situation in which you can indeed consider a Limblad master equation also starting from some phenomenological input. The idea is, in a sense, very simple. You have your particle. So this time the system are the center of mass degrees of freedom of a massive particle. So this is our S. And this particle is interacting with a gas background. So these are typically lighter particles making up a gas. And the idea is that the interaction goes as follows. You have, for example, this gas particle with a given momentum P. This vector P denotes momentum of the particle. It collides with your system. I remove this arrow in order to avoid confusion. I just put an S here. It collides with your system. Your system initially had a momentum small p. And what happens afterwards? Well, after the collision, this is again the system. These are again the gas particles. And the idea is that the gas particle which has flown in is flying out with a momentum which is p minus q. This small q is the momentum transfer in the collision. And as a result of momentum conservation, your system has a momentum p plus q. So from the viewpoint of the system, what do you have? If you consider the statistical operator of the system, which was previously, just to give an idea, had a certain probability to have a certain momentum value. Now, this state is changed as a result of this microscopic interaction event, which you do not describe in detail. You describe before and after, of course. Before and after. You see the effect, the net effect is a momentum transfer. So you go from a situation in which you have momentum small p to a situation in which you have momentum p plus q. But this quantity can be as well be written as the expectation value with respect to p, to rho s, acted upon a certain unitary operator, which is as I said, I put h bar equal to 1, okay, just to write a little less. This is e to the I q dot x. X is the position operator in the standard meaning, which acts as a translation in momentum space. So if you let this operator act on a eigenvalue of momentum, it sends this eigenvalue in another eigen vector corresponding to eigenvalue p plus q. Okay. But this is then a natural candidate for a completely positive map, because we have operator to the left and adjoint to the right, which describe the microscopic interaction events. So in a sense, of course, we are now simply guided by intuition. We just write down in a phenomenological way the equation, and of course one can pursue other approaches when one tries to, for example, using perturbation techniques, try to describe the interaction between massive particle and gas particles and see whether one can, in a sense, substantiate this approach. But by itself, it's for sure, we know if we come to a Limblad master equation, we know that it still describes a possible sensible physical interaction. So if these are natural candidates for Limblad operators, in this case are unitary operators, how does our evolution equation might look like? The time derivative of OS will have a contribution which I here neglect, which is due to the free Hamiltonian of the system. This would be the, so to say, the free kinetic term. I neglect it here simply because our idea is that we want to focus on the effect of these collisions on the dynamics. And what we will find that is that these collisions do induce a decoherence effect on position. So now this effect of this collision will show up as a decoherence effect with regard to the position of the particles. So this is the typical dynamics which might lead to a controlled decoherence experiment as has been performed in Vienna in the group of Zeilinger and Martin. Maybe you will mention this, maybe not, because of course this now go back to some years ago. But still is a typical experiment which you can indeed describe and test decoherence. So in this sense, it's also relevant in view of people which want to face alternative description of quantum mechanics, as it is the case for spontaneous collapse models, which effectively leads to the same effect, only with different rates. I will comment on this just in a few minutes. Yes. The position of this massive particle. As I said, the system is the center of mass degrees of freedom of the particle. Either you consider it a point particle, it is this position, or the center of mass if you want to put it down. Exactly, yes. Yes, yes. This will show up now in a minute. So, how does this time derivative might look like? We have to consider a Limblad contribution, neglect the free evolution since we want just to focus on the relevant part, and find the different replacements. So we said these Limblad operators goes over to the e to the I q dot x, so the generator of translation in momentum. What happens to the rate gamma k? Well, now k has become a continuum index. So this will be a probability distribution over the different possible momentum transfer, and I put in front of it also a rate, let me call it lambda. So this lambda gives the collision per unit time. This is the rate aspect if you want, and this takes care of the k dependence, tells you the probability to have a specific value of k, so to a probability to have a specific value of the momentum transfer. We have essentially everything, and in view of this, we also have to take into account the fact that the sum over k has to be replaced by an integral over the possible values. So with these ingredients, we can write down our master equation. We have e to the I q dot x to the left and to the right. Then you would have minus the 1/2 the anticommutator of the adjoint of the operator times the operator, but it's a unitary, so the identity, so it's simply minus rho s. Our rate is now P of Q multiplied by lambda, and the sum over K is now the integral over Q. So you very easily end up with this master equation, which leads to a semi-group composition law, with the idea that there is no memory in this setting because the different collisions of the gas particles do not depend on previous collisions. It's a natural approximation, at least as far as the gas is sufficiently dilute. But for a decoherence experiment, it has to be dilute, otherwise you simply wouldn't see anything. So it's a very natural setting. So one, of course, can check that this all has all the relevant, interesting properties. But on top of this, it's easy to see the decoherence effect in the sense that we can immediately obtain results for the position matrix element of our statistical operator. So, in particular, we can write down this equation considering as matrix element the position matrix elements, these are x and y, which end up to the integral over q, p of q, e to the I q dot x minus y minus the identity times x rho s of t y. So the point is that this map, this operator, acts by multiplication in this representation. In such a way, it's easy to find out the solution. The matrix element at time t in position between x and y is simply the matrix element at the initial time times a function which can be written as minus lambda t one minus, let me use this notation, phi sub p, depending on x minus y. Now I explain in a second what I mean. So this function phi of p is the Fourier transform of our probability distribution. Fourier transform evaluated at x minus y of the probability distribution of momentum transfer. So the Fourier transform of a probability distribution is typically called characteristic function associated with the probability distribution. So the dynamics is essentially determined by this characteristic function. So what we see is that if we look at the effect of these collisions on the position matrix elements, they act as multiplication by a certain factor. For the diagonal elements, nothing happens. So if x is equal to y, this quantity is equal to 1, so nothing happens. The diagonal elements are not affected by this kind of dynamics. This is also necessary in order to trace this solution. But what happens to the off-diagonal? Now, as a general feature of this characteristic function, one can see that the diagonal are suppressed. But in order to see this is in a more substantial way, let me consider approximation in which this is the characteristic function. So it provides the derivative provides all the moments of the distribution. Suppose that small momentum transfer are preferred, so that we only consider the lowest order moments. Suppose for isotropy that the first order moment is equal to 0, so essentially we end up with multiplying our initial off-diagonal density matrix expectation value in position for a function which is lambda t, and then 1/2 the second momentum of our distribution, plus in principle the contribution due to other moments, which we assume to be negligible, times, and this is the relevant part, the dependence on the difference between x and y, which here appears squared since we are considering the second one. So what happens is that off-diagonal position matrix elements are suppressed exponentially. So this is a way to describe a loss of visibility in interference pattern because off-diagonal matrix elements are suppressed. Then, of course, the microscopic information about what is the specific feature of the collisions, what is the relative ratio of the masses of the gas with respect to the mass of the flying object, all this information are now, in a sense, encoded in this rate, the number of collisions per unit time, and this and the second moment of your momentum transfer distribution. So the microscopic interaction are written there. And this tells you also that this viewpoint does not necessarily apply when you really consider, say, proper collision between massive objects, but also other interaction which can still be boiled down to random momentum transfer between your system and what you consider as an environment. So it's a kind of general picture. So, and the effect of this is a suppression of interference fringes. Let me write it in a very trivial way, but suppose this is the visibility of your fringes without collisions, then what you should see that depending on, for example, the gas density, the length of your interferometer and so on, you see a suppression of this kind. Of course, this is very naive, but just to focus on a picture. Okay? And what the last thing that I would like to say, you go from here to here due to the coherence, but you also go to here from here due to spontaneous localization model. There are different names for them. Let me write it. So the statement is that the same net effect comes both from a microscopic physical description or interaction, in this case, for example, the ground gas, or from an intrinsic mechanism, which, for example, you can express by means of this nonlinear generalization of the Schrödinger equation. So just to point to the fact that, and this will be for sure one of the topics touched upon by Professor Bassi, when they want to exclude or see whether the spontaneous localization models are compatible with experiments, they have to distinguish between possible decoherence rate due to physical effect and effective decoherence rates due to intrinsic localization. So the effect is the same, but the physics behind is quite different. Okay. Sorry? That would amount to come back to a picture analog to the one that I introduced before, so where you also have a distribution of times in this. You would still see it. Actually, there was a second part of the example, but I decided to skip it. You can introduce a similar model, but allowing, now let me write this master equation in a more compact way. It can be written as follows. I have this epsilon applied to rho, like the given operator is now the integral over q, e of q, and the action to the left and to the right. Okay, this is, as a whole, you can see it as a node. Minus rho itself, everything multiplied by. You can rewrite it as it is. Now, the point is, instead of this expression, I could put here a memory kernel of the type I introduced before, only a simplified version, if you want, in which I only keep the C number part, so the ratio between F and G, and then see what happens. And this modifies a little bit. But the basic effects still remain. What changes essentially is this part of the expression. So I will end up with another structure still related to the characteristic structure. So this is feasible.
You also wonder about what
then whether this is being caused by spontaneous localization or environmental decay. So that's very important. Are there any control parameters in the system or environment such that the decoherence depends differently on those parameters depending on whether it's the environment contributes or whether it's the insurance disease?
This I wouldn't expect. It's difficult to say, but I wouldn't expect. So, of course, there are different physical parameters which determine the, let's say, the overall decoherence rate. Let me call it the overall decoherence rate. But one, I mean, if I were to compare this model with another physical model, I could say, well, here I see a dependence, for example, on the gas density, which is linear in the argument of exponential and so on and so forth. The other physical model provides another dependence on the gas density, so that I could say to the experimenter, please perform these at different density and see whether which model is better. But the spontaneous localization models actually do not depend on a physical interaction. So the rate in that model cannot be affected by the fact that the gas is less or more dilute. So in this respect, it's difficult for me to fancy out that one can play with this. What you can compare is the overall rate with the overall rate. No, I think there aren't. The only thing that comes to my mind in this respect, there was recently some work about I guess by Budker and others. The idea was to introduce a technique which should, in a sense, these are dynamical decoupling techniques. And there they say something like, there you can distinguish between the effect of a dynamics coming from a physical description in terms, for example, a Lindblad generator and so on, from effects due to something which is an intrinsic effect, such as in spontaneous localization. Yes, but that's the only thing that comes to my mind, and so it's within a different setting, this setting of dynamical decoupling, and so yeah, this week. Okay, so then yes, yes, it's typically the case that you suppress it completely. So you need a lot of effort in order to see the transient. And in fact, the experiment which were able to do this go back to, say, something like 10 years. So what typically, so naively, one would say, okay, as soon as my massive particle is not flying through the vacuum, I'm not going to see anything on the, so the interference pattern will immediately get lost. Then, as a matter of fact, and this is the kind of dynamical effect that you described through the coherence, as a matter of fact, in principle, you should be able to see a transition between a full interference pattern and a reduced interference. But the transition is typically very quick. So any disturbance is immediately very effective. So it's an important result that one could manage to observe. No, but very quick, I means that as soon as, meaning that any small disturbance leads to loss of interference. For example, if the vacuum is not perfect, any residual gas in the thermometer would lead to, in this way. It's not a question of time. Of course, time also plays a role in that. How many collisions are going to take place during a typical run? Well, it will depend how big the interferometer is. So, if you want how long the time is that your massive particle has to interact with the gas. It will depend on velocity of the incoming particle and length of the interferometer. So plays a role in that respect. But in any case, they are short times. And what typically happens that just, so this is a question that should be better answered by experimentalists, but as a matter of fact, one would say that just 1 or 2 collisions and you're done. So which means that if you think really as particle as a massive object flying through, as soon as they experience 1 or 2 collisions, then they are lost for the interference pattern. They do not contribute anymore to the interference pattern. What do you mean by spontaneous now? Actually not. Of course, this could be a huge topic, but I just say the following. When I say that 1 collision is enough, it means that the strength of a single collision is enough. If you could soften the effect of a single collision, this will depend on the mass ratio and so on, then you could allow for more. Or if you had, a greater control in the apparatus, then you could allow for more. So it's not spontaneous. You wouldn't use the word spontaneous. The fact that maybe just 1 interaction is strong enough in order to produce effects which are so important as to wash out the different things is something different from saying that it's a spontaneous effect. It's just a question of strength of the interaction. In this respect, I always recall the experiment, the Gedanken experiment mentioned by Hyman in his introduction to the slits. Now, send light to one of the slits, then depending on the wavelength of the light, you might expect it. This is essentially the very same thing, if you want. I'm just speaking about momentum transfer. Now, not between photons and atoms, just between massive particles, but in the same state. So it will depend essentially on the strength of it. They are not effective. So they are no, in the essence, no collisions. Okay? So I'm terribly out of time, but still, if you could follow me, that is more important. Okay. So I go for part 2. And I will provide references for part 2 as usual. Later on in the afternoon, I will let them appear on the black. So part 2 is about non-Markovian. Of course, we have already touched upon the topic. I've prepared the ground, but now we really go to it. So non-Markovianity. This was meant to be a crash course. Now it will be a crash course. What I think important is to convey the main concepts. So we start with definitions and measures of non-Markovianity. The plural is due to the fact that I will point to maybe not just one concept, but a couple. So I start, the idea is to connect memory effects with the distinguishability of quantum state. So as a first part, I will speak about memory and distinguishability of quantum states. Because I guess this is the heart of the matter in the essence. What do we mean by distinguishability of quantum state? Suppose we have a source that can prepare 2 possible quantum states, say ρ1 and ρ2, 2 possibilities. And you can also think that ρ1 is prepared with a certain frequency, which is P1, and ρ2 prepared with a frequency which is P2. So that P1 plus P2 equal 1. So a certain fraction of times you prepare the 1, a certain fraction of times you prepare the other. And then you are allowed to make a single measurement and to infer what the state was. This problem is so-called one-shot, two-state discrimination. So what you do is here prepare, and then you measure. And you also consider a two-valued measure. So you have to decide what to measure. For example, you can decide to measure a certain projector P, and since we consider two-valued outcomes, the other element which, if you want, makes up your P of M is 1 minus. So what is once you fixed P and you associate to the detection of P, the fact that the state was rho 1, for example, what is the success of your strategy? So once you say that you decide the P, and if P is measured, you say the state was rho 1, what is the success that you actually can obtain? This probability of success, which depends on your strategy P, the projective listening sensor strategy of your measurement. How is given this probability? You can write it as follows: is the probability to measure pi given that the state was rho 1 times, so it is a conditional probability for, times the probability to have rho 1. This conditional probability, according to quantum mechanics, is the trace of pi times rho 1, statistical operator, and this is the original weight which we assume to be P1. This is part of your successful assessment. And the other contribution comes if you indeed measure 1 minus pi, provided that the state was rho 2, times the probability to have prepared rho 2. Again, this is the trace of 1 minus pi rho 2, and this number is P2. Now you can, for sure, you can say that this is for a fixed strategy. Then you can say, okay, now I change the strategy, so I vary the projection that I'm considering. And then, of course, this quantity is upper bounded by the maximum over pi of this possible strategy. And the point is that one has an expression for this optimal strategy, which goes as follows: is 1/2 1 plus the trace norm of P1 rho 1 minus P2 rho 2. I already introduced the trace norm in the first lecture. This is the trace of the modulus of these operators. Essentially, just to remind, if T is self-adjoint, the trace norm is the sum of the modulus of its eigenvalues. Okay, just and so this would be the general expression, which gives you the probability of success if you do the best that you can. So the best probability to determine the state is determined by a fixed factor plus a bias if you want, and the bias depends on the difference between these two quantities. Let me consider a simple but relevant case in which you assume that there is no initial bias in the preparation, in the sense that with equal probability you prepare rho 1 or rho 2. Then this boils down to considering 1/2 1 plus the so-called trace distance between the two states, which is, according to that expression, 1/2 their distance according to the trace norm. So this is a distance in the space of states, and the statement is: how good is your capability to distinguish among the two? Well, it will be all the better. So this is a bias in favor of your being able to distinguish. If you're not able to say anything, this would be 0. then your probability is 1/2, just by chance. You say it's the one or the other with equal probability, just chance. You don't have any proper information in order to distinguish among them. But the farther away they are in the space state, the better is your capability to distinguish among them. So there is a connection between distinguishability of states and this quantity which is called trace distance. This quantity, which is bound always positive because it's a norm, and according to this prefactor 1/2 is bounded by 1, it takes the value 0 if and only if the two states are exactly equal. And if they are exactly equal, it's impossible for you to distinguish among the two. So you can just say, well, it was rho 1 or rho 2 by chance. So we are 50-50 probability. And it's equal to 1 if and only if they are orthogonal, which means that their support is orthogonal. You need to consider the spectral representation. They belong to orthogonal subspaces. If they are orthogonal, you can find immediately a strategy which allows you to distinguish among the two. You choose this pi in the subspace of rho 1. Then if you have the answer 1, for sure it was the state rho 1. If you have the answer 0, for sure it was 1. So in this case, you have a preference strategy. So your probability of success is equal to 1. Now, in such a way, I have motivated the fact that this trace distance, this distance in the state space, is an expression of the distinguishability of two states in a natural procedure in which you prepare them and you can perform one quantum. Okay. So I have made this connection. Now, let me point to a couple of properties of this quantity which will be used later on. I put them here. Well, there are many properties, but I just mentioned the relevant ones. The first is that if you consider the distance between a state which has the form of rho 1 tensor in other given state sigma, and the distance with respect to a state which differ only in the first argument, then this is exactly equal to the distance between rho 1 and rho 2. So tensor product with a fixed element doesn't make any difference. Why? It is subadditive with respect to the tensor product in the sense that if you consider the distance among states which are of tensor product form with different contribution, this is upper bounded by the distance among the first two and the distance among the other two. So this is upper bounded by the distance between rho 1 and rho 2 plus the distance between sigma 1 and sigma. This is the key ingredients that we will need later. Now we go for the most important property of the trace distance in our perspective, which is how it relates to the action of a well-defined time evolution. And the well-defined time evolution is, in our wording, and according to what comes out of an analysis of quantum dynamics, a CPT method. What happens in that setting? Suppose we start from a couple of states, rho 1 and rho 2, and we want to see, given that they have a certain distinguishability at the initial time, then you let them evolve with the same map phi t, here and here, and you can ask the question, what is the final distinguishability? And if I write P of t, means that this is a CPT map. Okay? Now, what happens? As a matter of fact, suppose you, in a sense, describe the state with these simple circles. After a certain time evolution, you'd better describe them in a more fuzzy way. So that if you have rho 2 at time t, so the transformed according to the map, and rho 1 at time t, their distance has to be smaller. What I mean by has to be, this is a mathematical proof. So, trace distance is a contraction under the action of CPT maps. Let me say a few words. So the picture tells you that the idea is that somehow you start with two states and they have a certain distance in the state space. And this distance tells how good you can perform if you want to distinguish them with a single map. Then you apply a map, which we assume time dependent, but the important fact is that once we fix the time, it's a completely positive transformation. This affects the state in such a way that they are less distinguishable. So according to this distance, they get, in a sense, closer to each other. Of course, there are special types of maps for which this doesn't happen, and you can imagine which are these maps. These are the unitary transformations. Because in the essence, as is written here, trace distance depends on the modulus of the eigenvalue, and this is left untouched by a unitary transformation. So this quantifier is unsensible to a unitary transformation. It just takes track of transformation, which are the one we are interested in, if you want, which are proper, not proper, I mean, also a unitary map is a proper CPT map, but those which can be related to a dynamics, which is in a sense non-trivial, non-reversible. And this is actually a theorem, and in the theorem, you actually simply need positivity and not complete positivity. This is just to be precise. Now, we are prepared to introduce the idea of what might be a notion of memory in quantum mechanics or of Markovianity, as it is nowadays said. Now, let me do this also by means of a kind of a picture. Suppose we have a time t equals 0, a certain distance, then we consider a later time s, and an even later time t plus s. Yes, please. Yes, for sure, in the sense that also the relative entropy is a contraction under CPT. So in this respect, there are different quantifiers that might play a similar role. In this respect, the choice of trace distance, well, but maybe we can discuss later on otherwise. For sure, the answer is yes. You can consider other quantifiers which in this respect behave in the same way, so that there are also possible indicators of non-Markovianity according to the viewpoint that I'm going to introduce now. So the idea is that we start with two initial states, say, time was here. So rho 1 at time t0, rho 2 at time t0. If we go from 0 to s according to a well-defined dynamics, what can happen? From 0 to s, they can only get closer. So I have to write rho 2s, rho 1s, and getting closer according to the distance. But what happens when I go to a later time? Now, suppose, for example, I consider a semi-group evolution, then what will happen is that they get even closer as time goes by. So the initial distance was a certain amount, which has to be below 1, but up to 1 can be whatever. At a later time, they get closer and closer and closer. So as times evolve, they get closer and closer, which means that with evolving time, the effect of the interaction with the environment is to lose the capability to distinguish among different states by performing a measurement on the states only, because there's been interaction with the environment. Such a situation is associated to lack of memory. And then you can imagine how we introduce memory. And to save time, let me use the very same picture. So I put the writing no memory a bit more to the left. another situation which might appear is the one in which, according to the first transformation, the distance is reduced, but then it grows again. It grows again. And this is good. This situation is associated to memory. So the idea is that we speak about a kind of memory effect when our capability to distinguish among states can grow again along the time evolution, which means that some information, I will come back to this later on, but some information that got lost in the interaction with the environment and which was necessary in order to perfectly distinguish the states is now coming back. That's the idea behind it. And yes, of course, now I've taken two fixed time points, then we can go. Now, let me stress the fact that it can fluctuate, but cannot go, the distance cannot grow beyond the initial value. So you have to pay attention not to go too high, neither too low, but this we will see later. So consider the example of quantum dynamical semigroups, the one that we know. Well, in that situation, what happens? We know that we have this composition property. So if you want to go from time 0 to time t plus s, it shouldn't make a difference whether you stop or not. The map driving you from here to here, as I drew yesterday, is the same that you obtain if you first go from 0 to s and then from s to t plus s. And so what happens is that the distance between two states at time t plus s, so rho 1 at time t plus s and rho 2 at time t plus s, can be written as the distance between the map phi of t applied to rho 1 at time s and phi of t applied to rho 2 at time s. But this map is a CPT map. Trace distance is a contraction. So this quantity is by necessity smaller than, well, I try to stay within space, the distance at time s. And this is true for all s and t positive. So the effect of this composition is that in order to move forward in time, you apply another map. This is due to the divisibility. And you see that divisibility is enough to have a monotone contraction of the trace distance. Actually, divisibility both in the sense of positive maps, because this is enough for the mathematical theorem, and in sense of completely positive maps. So whenever you have a composition law which warrants that the different ingredients in the composition still retain the property of being positive, completely positive, you obtain a dynamics which in this respect does not exhibit any memory, because the capability to distinguish states gets lower and lower with elapsing time. So a typical situation would be coming back to your relative entropy, consider a kind of Boltzmann-like equation. What happens that all states tend to a fixed stationary state, for example, the thermal state corresponding to given temperature and mass, and they do so in a monotonic way, so the relative entropy goes to 0 relative with respect to this reference state. So all states get closer and closer to this final stationary state. Of course, this is just one special example, but somehow it's the idea behind the approach. And I would like to stress that actually this basic idea is due to Heinz-Peter Breuer with his collaborators in 2009, LC and Pilo, and led to a simple but I find very meaningful idea that led to many development activities. Then I will write you some references as promised. Okay. Okay. Goodbye. See you in the afternoon.